Hi everyone, today we have a few friction problems for forces in AP Physics 1. The AP is coming up soon, so let's get started. In this first problem, we have a man pushing a book against the wall, and we're trying to find the minimum force to keep the book from falling. And we're given that the static coefficient of friction is 0.15. We're also given that the mass of the book is 1 kilogram. So let's start by drawing our free body diagram. We have a force that the man is using to push the book against the wall. We'll call it F. We have mg of the book. We have Fn of the wall pushing back on the book. And we have some frictional force pointing up, as the book naturally wants to fall downwards, so naturally friction will oppose it. Let's start out by writing our sum of the forces. In the y direction, we have FF minus mg. And if we want the minimum force to keep the book from falling, we're going to set this equal to 0, as anything below 0 will cause the book to fall. So, FF is also equal to Fn mu s, or the static coefficient of friction, and we could add mg to the other side. Dividing by mu s, we get Fn is equal to mg over mu s. In this problem, we know that this force F and Fn are equal to each other because in this frame, the book is not accelerating to the left or to the right. So we can say that Fn is equal to F. We can now replace Fn with F and set it equal to mg over mu s. By plugging in for m, which is 1, 10 for g, and 0.15 for mu s, we get that the force required to keep the book up is 65.33 newtons. For problem 2, we have a 20 kilogram child that is sitting in a 5 kilogram sled that is resting on flat ground. So we have our 5 kilogram sled with a 20 kilogram child in it. The coefficient of static friction between the sled and the ground is 0.1. So mu s equals 0.1. And the coefficient of kinetic friction is 0.05. What is the minimum horizontal force required to start moving the sled while the child is sitting in it? Okay, let's look for keywords in this problem. We're looking for the minimum horizontal force required to start moving the sled. If we want to start moving an object from rest, we're going to want to use the coefficient of static friction. So let's start off by drawing our free body diagram. We have some force F pulling the sled, mg, and we'll combine the mass of the sled and the kid for this mg, some force of friction opposing the motion, and also a normal force Fn pointing up. Let's write our sum of the forces. Sum of the forces F in the x direction equals some force F minus the opposing force of friction. And if we want to know the minimum horizontal force required to start moving it, we'll set this equal to 0. Adding F of F to the other side, we get the force is equal to the force of friction, which is also equal to Fn mu s. We know that F of n is equal to mg because the sled is not accelerating upwards or downwards. It's staying in place in terms of the y direction. So we can set Fn equal to mg, and then we multiply it by mu s. And plugging in, we get the mass of the kid in the sled, 25 kilograms, times 10 meters per second squared, times our static coefficient of friction, which in this problem is 0.1. And this equals 25 newtons. The next part of the problem asks us, when the child jumps off vertically from the sled, assuming the same force continues to be applied to the sled, what is the sled's acceleration immediately after the child jumps off? Let's draw another diagram for this one. We have our sled with the child that has jumped off it, and we have our kinetic coefficient of friction, which is 0.05, and we're asked to find the acceleration. Let's draw our free body diagram. This time, we don't have to worry about the kid, as he is not in the sled. So we have the mg of the sled, the same force from part A pulling it, some force of friction opposing the motion, and then Fn from the ground. Let's start out by writing our sum of the forces. Our sum of the forces in the x direction is equal to F minus the force of friction, and this is equal to ma, since the sled is accelerating. We can isolate A by dividing over the mass to get F minus the force of friction over m. Similar to what we did in part A, we can set Ff equal to Fn mu k. We're using the kinetic coefficient of friction because the sled is already in motion in this problem. So rewriting this, we get A is equal to F minus Fn mu k over m. We know that Fn is equal to mg because the sled is not accelerating upwards or downwards. So plugging in, we get A is equal to 25 newtons, the force that we got from part A, minus the mass of just the sled, which is 5 kilograms, times g, which is 10, times the coefficient of kinetic friction, which is 0.05, over the mass of the sled, which is 5. And this is equal to 4.5 meters per second squared. Nice. Question 3. A 2 kilogram block is sliding on a horizontal surface. The coefficient of kinetic friction between the block and the surface is 0.2. So we have our 2 kilogram block that is sliding on a horizontal surface with the kinetic friction coefficient being 0.2. Two forces are applied to the block as it moves. Force A has a magnitude of 10 newtons and acts at an angle of 30 degrees above the direction of motion. So let's assume the direction of motion is to the right in this problem. So force A has a magnitude of 10 newtons and acts at an angle of 30 degrees above the direction of motion. Force B has a magnitude of 15 newtons and acts at an angle of 5 degrees below the direction of motion. So we have force B, magnitude 15 newtons, and acts 5 degrees below the direction of motion. And of course, these angles are not drawn to scale. We're asked to find the normal force acting on the block in part A. Let's start out by drawing our free body diagram. We have mg of the block, our force A and force B pulling the block to the right, and we also have some force of friction opposing its motion to the left. And finally, Fn from the ground. If we want to find the normal force of the block, we're concerned with the forces acting in the y direction. So our sum of the forces in the y direction is equal to Fn plus Fay, since force Fa is acting in the y direction, minus mg minus Fby. And since the block is not moving up and down, we'll set this equal to 0. Let's subtract and add some of our forces over to isolate Fn. We'll subtract Fay, add mg, and add Fby. 'Fby. 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 ' When we're considering the y component of the force, we'll use sine theta if we're given that the angle is above the x-axis, and if we're trying to find the x component, we'll use cosine theta. So for Fay in the y direction, we'll have negative 10 newtons, which is its magnitude, times sine of 30. mg is simply the 2 kilograms times 10, and for Fby, we have 15 times sine 5. Simplifying this, we get Fn is equal to 16.31 newtons. Moving on. Now we're asked to find the acceleration of the block. Since our acceleration is in the x direction, we're concerned with the forces in the x-axis for this problem. So let's write our sum of the forces in the x direction. We get Fax plus Fbx minus the opposing force of friction, and we'll set it equal to ma. Let's isolate A by dividing over the mass to get Fax plus Fbx minus f of f over m. Now, like we've done before, we can set f of f equal to Fn times the coefficient of kinetic friction, since our block is moving in this problem. And we can rewrite this to account for our x components. So, again, if we're concerned with the x direction and we're given an angle above the x-axis, we're going to use cosine theta for our x components. So Fax becomes the magnitude of Fa, which is 10 newtons, times cosine of 30, plus 15 times cosine 5 for Fbx, and we subtract Fn times mu k. We found Fn in part A, which is 16.31, times the coefficient of kinetic friction, which is 0.2. All of this over the mass of the block, which is just 2 kilograms. Simplifying this, we get A is equal to 10.17 meters per second squared. Thank you for watching. I hope this helps.